I'm very thankful to be given the opportunity to talk about my work. Um, I've given a little bit of um, like a tentative title. Let's put it this way. This is the dream or the target that we are trying to do. With all the recycling, the needs of plastics, we are trying to see upcycling possibilities for polyolefins, being in the Houston area. So how can we take polyolefins and transform it into polymer film capacitors? And I'll tell you, in more detail what I mean for high energy storage devices. This is really the work started with Diana Cousins. Sumaira Rani did a lot of the work, but there's also Dr. Maninderjeet Singh and Professor Robertson. Myself, we have a Welsh Foundation project on recycling, but that this is sort of related to that work, but this is mostly work that I had going on even before that. And I want to thank Dow for funding related to Diana Cousins' research. So let me see if I can move to that. So if you actually look in the literature, there's a lot of interest in it's a sort of a race to develop high energy density solid state capacitors. These are flexible. These would be flexible, should be flexible. And you can see what state of the art is getting us, and this is already a few years old. So like 150, 130 kind of joules per cc, that's a lot compared to biaxially oriented polypropylene. BOPP, the industry standard, is more like 2 to 4 maximum joules per cc in packaged form. But in these examples, mostly use ferroelectrics, and ferroelectrics have a significant disadvantage in that the energy loss, because you have domains of aligned dipoles and so on, to move total domains around with grain boundaries, friction and all that is very wasteful in terms of energy. So the energy loss is very high, and these would be very hard to make commercial, for long-term storage and things like that. So we thought, we've been working on energy storage for a while, but just to tell you that already dielectric capacitors are in use, for example, in electric vehicles. The reason is that there is a lot of power fluctuations. When you accelerate, when you decelerate, all that energy there's a lot of voltage and power fluctuations, and capacitors, as you can know, can stabilize power fluctuations. So they are actually part of grids and so on. But they are mostly like electrolytic capacitors and ceramics and so on. Our interest is, as shown here, in these organic uh, capacitors. So let me see if I can get a red pen. Okay, so we are interested in polymeric based capacitors. Compared to ceramics, ceramics have low voltage, they break down easily, then they're not flexible, they're mechanically, they can crack. So that's the problem when they have they don't have what's called graceful failure. Polymer capacitors have graceful failure. They don't just immediately fail, they fail in like bits and pieces as time progresses or as the voltage increases. So So here is a table of materials. What really matters, as you can see in this equation, the energy density is a function of permittivity or dielectric constant, and the square of the breakdown voltage determines the maximum energy you can store. So there's two quantities, dielectric constant and breakdown voltage. And if you can look in this chart here, you see polymers have low dielectric constant. So the permittivity is low, but the breakdown is high. Same for most of the other polymers. But take barium titanate, a ceramic, it has high dielectric constant, low breakdown voltage. So really, no single material has the combination of high permittivity, high breakdown. And ideally, you want to make like a marriage of the two, meaning a hybrid material, hybrid polymer capacitor to capture these properties. So if you look at this plot, this is called the Ragon plot, power density versus energy density. Yeah, capacitors are here. They can store, they can charge and discharge very fast, and they have very high power density. That means energy per unit weight. On the other hand, they store relatively little energy, at least currently, compared to batteries. Batteries are slow to charge, discharge. You know that from your cell phone. It takes overnight sometimes to charge, and discharge is also slow. So what we want to take is capacitors, move the capacitor, sort of um, performance from here to here, where they can compete on the low end of supercapacitors or batteries, right? The other big thing with capacitors is the charge discharge being fast is very important. I mean, for example, think of an EV. If you have an 18-wheeler and you're trying to go from 60 miles per hour to a red light stop in 30, less than a minute, how do you dump all that energy, which currently goes into brakes and heat and friction? Your battery cannot accept that much energy that quickly. But if you have a huge bank of capacitors, they charge and discharge in seconds, picoseconds, nanoseconds. So you can dump a lot of energy very quickly. Light turns green. You step on the gas. Now, all that energy can be dissipated very quickly, whereas a battery cannot give out that much energy that quickly. Electrocapacitors are somewhere in the middle over there. So I think that's what's currently, in fact, used in the EVs right now. But we see the next phase, being capacitors. So when you charge a capacitor, as shown here, then you discharge it up to the point of breakdown. You see the green area is the air storage of the energy storage in the capacitor. The red is the loss part. So if you return back to zero field and there's residual displacement in the dipoles in the that did not fully recover, you have lost this much energy in pink, whereas the green is the energy. So we want to maximize the green region. So now the choice of materials, okay? As I said, ferroelectrics, as you see, have domains, and that the area under the hysteresis of this curve, that's the loss. So you lose energy. So if ferroelectrics are high, but the charge discharge is not favorable. A linear dielectric has no loss. It linearly goes up and down with electric field, the energy displacement vector. So we want these, and maybe it's something in the middle that we can be comfortable with. The important point is, how is the energy stored? So there is all levels of energy storage. Electric polarization. Dipoles can get polarized if there are dipoles in the system by the apply. When you're charged, you align the dipoles. You align ionic more material. For example, ionic liquid could be oriented. These days, they're making polymerized ionic liquid, which is very cool. So that's a very good candidate, I would say. But even interfaces can hold charge because of dielectric mismatch between two materials at the interface. I'll show an example of this that we looked at, and we think there's actually much potential for this as well. All right, so it's a balancing act. You can there's all these parameters you want to optimize. You want it to have durability. You want it to be flexible. You want it to have, for miniaturization, you want to make it really thin. You want, low heat loss and so on and so forth. And people have tried in this area a lot of strategies. They've modified the polymer. This is by far a huge effort. Blend polymers to combine the best of two properties. Add inorganic, and this one, as I said, the main idea was to enhance the dielectric constant. Barium titanate has very low breakdown voltage, but extremely high dielectric constant. So, and then multi-layer films is sort of the latest theme. I'll talk a little bit about this as well, where you can have, as I said, the interface can create dielectric constant mismatch that can store energy. And I think this is actually the strategy going forward. It also resonates with the theme of multi-layer packaging and polyolefin recycling. All the Lay's potato chips bag and all that have multi-layers. Can we actually take those multi-layer films and use them as capacitors? They already have a metallic layer in them for the barrier, for the gas barrier properties. All right. So let me first start with the dielectric constant. There's two parts: breakdown voltage and dielectric constant. It's linear in dielectric and typically square in breakdown voltage. So let's look at dielectric constant first. Then this is our literature. Okay. So you can see polyimide as you reduce, and we are talking now in a regime which is really thin. So sub-micron thickness is the region of interest. So you see, as you decrease film thickness, the dielectric constant goes down for a glassy amorphous polyimide material, for instance. Uh, Also for semicrystalline, PVDF. As you can see, as you reduce thickness, as I said, this is nobody's really looked at these in great detail in the submicron regime. People have shown it for 100 micron down to 10 micron. Actually, energy storage goes up. I'll show you, but not in the submicron regime, which is we want to make them really ultra thin, for example. So how does the mechanism, what's the mechanisms? Different. This is already a very old slide. It is not entirely accurate, I would say, but generally in glassy polymers, polymers well above TG, PMMA, polystyrene at room temperature, electronic, rubbery, you can have thermal, and plastic flow, if it's well above TG, then you can have electromechanical breakdown. Polymers, as I said, if ceramics, you have a straight through breakdown pathway, but polymers, you have an electron avalanche method, and people don't fully understand it, but they've imaged it and shown that it's like a fractal tree. And as I said, that our interest is, can we take this avalanche breakdown in ultra thin confined submicron films? Can we somehow prevent this avalanche from happening rapidly? And maybe that is a strategy to enhance breakdown. Here you can see that simulations already show that in thick films from 100 micron down to 10, 20 micron, the energy storage or the breakdown voltage can increase. So I wouldn't be telling you all this if we didn't actually have data to say that this actually works. So take a look at this one. Now we're in the going from submicron. This is dielectric strength, which is the breakdown voltage. And this is film thickness. We put electrodes on two sides, measure the breakdown in a particular way. It's called the Weibull plot. And you can see above 1 micron, you're at about 250 volts per micron. But below a micron, it goes up dramatically. These are all different molecular weights of the PMMA film thickness, different 600K down to 16K, all follow sort of a universal curve. So that's great. If you look at the ratio of the thinnest film, which is about maybe 150 nanometers, to the 1 micron or 2 micron film, it's about a factor of 10. So 10 times higher breakdown strength. That is actually very impressive because the energy goes as the square of the dielectric strength, which means we should think of 10 squared, which is 100. So presumably an ultra thin film of 50, 100 nanometer has 100 times more energy storage capacity compared to these microns thick film. So this was just recently published. And we have shown that for polystyrene and one or two other polymers. It doesn't work well with rubbery polymers, but for reasons I explained earlier. But let's take another example, block copolymers. And these are polystyrene PMMA lamellar forming diblocks. When you cast them from a solvent like flow coating, spin coating, they are in a disordered state because the solvent rapidly evaporates, it vitrifies the disordered state of the block copolymer, and you get energy storage like 3 joules per cc, as you can see here, in the disordered state. Okay, all the red lines are different molecular weights in the disordered state. All you have to do is put it in a vacuum oven and heat it, above its glass temperature, go up to say 160 C, hold it for a couple of hours, and it will go to the ordered state, which is microphase separated. And you will see that amazingly, the blue curve now is the annealed lamellar state. We apply the E field perpendicular to the lamellae. So electrode will be here and here. But now, because of remember what I said about interfacial polarization, all these PS and PMMA, each block is, for example, PMMA, PS. It's the interface, a dielectric mismatch that contributes to the interfacial polarization. And with it, the energy storage density goes up from almost to 5.5 and so on. So that's pretty impressive that just by taking the same material in the disordered state, it's much lower. This really proves that interfacial polarization is a big mechanism for energy storage. So I'm kind of running through examples of what we've done in the past. These are all glassy polymers. They're not polyolefins. But to give you a sense of what we have been doing in this field, we also looked at putting now ceramic particles. So in this example, we started putting hexagonal boron nitride, graphene, and so on other nanoparticles. But the most impressive one, which was again, what is commercially available is mica. So we took ultra thin mica sheets and put it between PMMA and PVDF and put electrodes on the two sides and measured the breakdown. So it's really like a two-dimensional mica sheet. It's a pretty macroscopic. And this worked really well. Look at the energy density. We are at 75 joules per cc compared to 6 in, pure block copolymer. And in BOPP, it was more like 1 and 2. So we are like 75 now. So it's behaving like a real energy storage device. If you look in the literature, all these advanced materials and other high impact papers, maximum was around 35. I'm talking non-ferroelectrics. Ferroelectrics go higher, but they lose a lot of energy. So you see, we are more than double the sort of world record with the non-ferroelectrics at this point, simply by inserting 2D ceramic sheet at the interface. And by the way, there's a lot of work that's been done where people have looked at polymer nanocomposites where they put silica particles, spherical particles, polymer grafted silica particles, but all spherical or even rod-like geometry, and they don't get anywhere close to this. In fact, the breakdown voltage, dielectric constant will go up because you're adding an inorganic, but the breakdown voltage actually goes down with these spherical and rod-like particles. The sheets is different. The 2D sheets actually effectively block the Z vertical breakdown directly by having it's like a physical barrier, and it's a large mica sheet. So that's what we think is the reason we are so much higher. So my point is that the dimensionality, two-dimensional filler is the way to go in the future for capacitors. As I said, a huge amount of work in nanocomposites with spherical particle. It does not do well on the breakdown voltage, and so the energies to breakdown is low. So you lose out on the square of the breakdown voltage, but you gain on the dielectric constant. You don't gain much, but with 2D sheets, you gain. It's a win-win situation, and that's really the sort of difference we have done here. So, and by the way, the amount of filler you add is like 1%. A sheet, 15 nanometer sheet is no more than 1% of the mass of the capacitor, whereas the previous studies, the filler would contribute to like 30, 48% of the nanocomposites. And even then, only dielectric constant went up, but the breakdown would go down with increasing filler. All right, so I hope I've convinced you that with glassy polymers, block copolymers, hybrid 2D material interfaces, there's a lot of potential. We wanted to stretch this to see for polyolefins if we can think of taking all the waste plastics or multi-layered plastics that's out there and think of new life for them in terms of energy storage for capacitors. So you're all familiar with polyethylene structure, polypropylene, linear low density polyethylene, high density properties are listed here. And so the idea is to take these and see if the crystallinity will make a big difference to what we showed so far. Um, so the question is, will film confinement, as I showed, decreasing below submicron, what worked for glassy polymers, is it going to translate to semi-crystalline polymers, in particular polyolefins? It's been studied in the bulk here. As you can see, people have taken polypropylene with the different nucleating agents or adding more and more nucleating agents. You can increase the beta phase. And the beta phase, clearly you can go from black to the green, where increasing beta phase volume fraction. So there is some precedence that controlling the not just the crystallinity, but the type of phase can help you boost the energy density. These are bulk films. In thin films, people have speculated on crystal orientation effects, flat on, edge on. If you get ultra thin, including our own work, we have shown that you go from spherulites that impinge on each other to something like dendrimers. And the general idea is that, morphology, controlling the lamella orientation, etc., could be important. All right, so now coming to what we do, I'm going to show you results in two categories, polypropylene, polyethylene, okay? So we cast these films from heated Decalin solution. It dissolves well. You wait a half an hour, 1 hour, it'll be, like a proper polymer solution. whether it's polyethylene, polypropylene. You can also take metaxylene or no, orthoxylene, heat it up to 140, but Decalin seems to work better. We have to improvise. We have to have a substrate that is heated, okay, because it can't immediately, you don't want it to cool right away. It should cool down slowly. The solvent should evaporate slowly for uniform film thickness. We have this thing called flow coater. We take films and we can, by changing the speed of drag of the polymer solution with this blade, we are able to create films with step gradient in film thickness, as you can see from 80 to 400, just by changing the speed in steps. And this is very cool because you can measure on a single substrate. The bottom could be aluminum electrode on silicon wafer. And so you can measure simultaneously, on one single chip, all the breakdowns for different thicknesses, okay? So I used to run the NIST combinatorial method center. These are the kind of techniques we developed. We have a large number of papers on this sort of flow coating method to make polymer films, to study adhesion, crystallinity, height, you name it, phase behavior, block copolymer assembly, and so on. All right, we developed a method when I was also at NIST in my early days, where you stretch an elastomer, put this film on it, and if you compress it, it will buckle, and the wrinkling wavelength gives you the Young's bending modulus. Very simply, all you need is an AFM or microscopy, and you can get it. We measure dielectric breakdown as shown here, dielectric permittivity, this is the dielectric constant, and we look at the morphology with optical and AFM. All right, so let's start with polypropylene. I mean, just to give an example, this is what the film looked like, film height. This is the thickness as a function of the speed of flow coating. This is called a flow coater, where we drag it at different speeds. Point is, we have very nice linear behavior. So this is the different concentrations going from low to high and different speeds. The combination of solution concentration, with one concentration, you'll make one set of film, like the blue. Increase the concentration, you make the orange. Okay, so this is how you make, it's called the high throughput approach. Then you can study, of course, the DSC properties and so on. Everyone may know that, pptm is about 166 in this case, as you can see from the DSC endotherm. Okay, now what happens to the morphology of these films as we have different thicknesses? And this is just showing you 540. This is now late stage crystallization behavior. They initially start out by forming spherical spherulites around these nucleation points. But these the spherulites grow and they impinge on each other and they form these kind of Voronoi tessellation-like patterns. The 312 shows you very clearly. These are kind of, pentagonal, hexagonal, and all kinds of interesting geometry. Essentially, you have crystal grain boundaries at these interfaces. As you reduce the film thickness, they get larger. It's not really larger, but they get more defined. And ultimately, below 100, you can see the number of nucleating densities increases. This is interesting in its own right to study. I'll show you just the result, but we can contemplate why it happens. And then ultimately you get fibrils. When you get down to 25, 30, 40 nanometers, you're getting polypropylene fibers more than because it's not forming continuous film. All right. We have a technique called GI wax that we use at Argonne National Lab Advanced Photon Source.
I'm on a Zoom call.
Yeah. Can you hear me? Hello?
Yes, we can.
Okay, good.
Yes.
All right. Okay, so GI wax, we go to Advanced Photon Source, which is a synchrotron at Argonne National Lab near Chicago. And at the grazing angle of incidence, you can determine the diffraction peaks, okay, in GI wax. So you get all these peaks that correspond to different, the crystal orientation and structure and so on. And we can calculate the degree of crystallinity. If you look on this box, 64, 60, 60-ish is kind of polypropylene, even though the bulk degree of crystallinity. What we find is that when you get below 100, you can get a significant enhancement. And we think that has to do with the confinement-induced alignment of the spherulite in the plane of the film. But if you go too low, it gets, it suppresses the crystallinity itself. Okay. So there's an optimum window of, aligned and high degree of crystallinity. And so you can expect the modulus can go up. We also measure long period and so on, interlamellar spacing, etc., as you can see. All right, just to show you, we measure with the C-beam technique. C-beam is a strain-induced elastomer buckling instability measurement method. As I said, you take a PDMS elastomer, stretch it, put your polymer, glassy polymer or semicrystalline polymer, PP film, let it go, it will compress it. You'll see the wrinkling wavelength, and we have an equation to calculate the Young's modulus, bending modulus. So you can see the modulus is significantly enhanced in ultra-thin film compared to the thicker, half micron kind of film because of morphological changes. I think the steep upturn happens when the when the lamellae orient because of confinement, in the film thickness direction. All right, so this is the modulus enhancement. Then we measure the breakdown strength. That's the one of interest. Dielectric breakdown in blue with the modulus on the red. And you can see the dielectric breakdown again goes up at 37 nanometer compared to 350. We are 15 times, the breakdown voltage is 15x higher than 350. Since energy goes as square of breakdown voltage, 15 squared would be 225. So basically, in principle, your energy storage in a ultra thin film is over 200 times that of the half micron film. Okay, energy density, that means per unit volume. All right. So the correlation to the modulus is actually very dubious, because I'll show you in the next example. All the glassy film, as you reduce film thickness, people have measured TG as a function of film thickness and modulus and shown that it always drops below, 100 nanometer because of film confinement. So the modulus enhancement is primarily because of the high degree of crystallinity that orients. Okay, so this is only true for high crystallinity block polyolefins, I would say. I'll show you the next example. LLDP, it actually drops, but the breakdown voltage still goes up. Okay, so these two are actually uncorrelated, even though they may appear correlated, they are not really correlated. So this, don't take the red, mechanical property is not correlated to the breakdown we think at this point. All glassy polymers, modulus goes down. The LLDP, I'll show you, also goes down, but the breakdown voltage goes up. All right. There is nothing we can do with the dielectric constant. It always drops with film thickness. The loss tangent increases a little bit. So you may think at this point that, well, if I lose 30% dielectric constant in the permittivity part, then the breakdown goes up. Maybe they kind of cancel each other. There's no net energy enhancement. That's not true, because the voltage enhancement was much larger than this 30% drop of dielectric constant. And so here, if you calculate the product of the linearly increasing or decreasing permittivity with thickness, but the, sort of very sharply increasing breakdown strength, you still come out winning. You can see that 250 nanometer, your energy storage might be like 5 or 6. That's consistent with BOPP as we know it. But of course, we don't biaxially orient it. We could try to do that, but making ultra thin BOPP would be really difficult. But as you decrease film thickness, we're getting up to, in this one example, even up to 100 joules per cc. Let's say 50, 60 is kind of more the average realistic, but it's going up very sharply. All right. But that's still, if a big increase from, 4 or 5, so factor of 10, like I was saying. So this is very, it would have been 200-ish if it was only breakdown, but you dropped 30% because of dielectric constant. All right. Okay. So this is polypropylene. I will, in the interest of time, quickly move on to polyethylene. Just showing you LLDP. Okay, these are the optical pictures showing you how the morphology, changes. It's very cool, kind of pretty. You can then look at AFM, the same thing. You can see them more topographically, or, you can get the phase contrast, mechanical property. If you look at the nucleation density versus film thickness, the nucleation density is the red. So thin films have high nucleation density, and then it rapidly drops off. So they make very many nuclei. And because they make many nuclei and these grow and they impinge on each other, they can only grow that much. So the spheroid ultimate diameter before they impinge on each other is very small. In thick film, the nucleation density is lower, but the spheroids can therefore grow to larger dimensions and then impinge on each other. But somehow, this combination of high nucleation density with low spheroid diameter is giving us the high breakdown strength. As I said, we see it also in glassy, so I'm not sure it is related to crystallinity or not, which is interesting. Again, for LLDP, linear low density, the dielectric constant, as I said, nothing you can do about it. It drops here, it drops in polypropylene, polyethylene, it drops below 150 nanometer. So this is not, in our favor. This is actually how we measure breakdown strength. We increase the voltage. Any one of these is a different thickness. Okay, so you can see the thinnest one is this red one with a very steep curve. The way you measure this is called a Weibull plot. You increase the breakdown, you increase the applied voltage at a given rate. So like 25 volts per second, and it will go from low voltage to high voltage, and you measure the current that's going through the dielectric material. Anyway, the 66% value of this failure is reported as the breakdown strength. Once again, in LLDP, you can see the ultra thin is about 4 times enhanced compared to the thick half micron kind of thickness. It's not as much as polypropylene, but it is still a factor of 4. Polypropylene was going 10, factor of 10 enhancement. Um, so these are just order of magnitude estimates, but just to show you that poly LLDP also, if you want to recycle it for energy storage, you can the product of the square of the breakdown voltage times the loss component, the permittivity still increases. So you're up from 3 joules per cc to about 12, 13, 14 joules per cc. Actually, it gets up to 18 in the best case. So not bad. It's still 18 divided by 2 is about 8, 9, so this is still very attractive. Okay. But here you can see that the modulus drops. Okay, this is what I was saying. Polypropylene is the only polymer where modulus increases as well as energy density increases. All the other polymers, glassy polymer, block polymer, LLDP, anything that is glassy or amorphous with low crystallinity drops. So there's probably too little crystallinity to orient and align as you decrease film thickness in LLDP. So it behaves like the other systems we have studied. Anyway, the point is that these are not correlated. Mechanical property does not seem that much correlated to the energy density storage. We think it's related to free volume and chain packing, chain orientation and packing and confined film thickness. So this is more or less, one last thing. So if this is really true, what I'm saying, I put my student to the test and said, look, a single 50 nanometer film should have a lower energy breakdown strength and thereby energy storage compared to two stacked films of that add up to that same thickness. Indeed, it's true. So you can see that the modulus also plays that same game. As I said, but it's not really connected. But if you want mechanical strength, if you stack two polymer films in this ultra thin regime that is the same thickness as a single film, modulus is much higher. It goes from 50 to 100, doubled. All right. Same with a breakdown voltage. The 60 nanometer is down here 900, and here this is about 12, 1400 if you make the ultra thin stacked bilayer. All right. So already we do that, and there's this extrusion technique that for like 3M makes these multi-layered, multicolored iridescent film. That was a Dow technology, and they make films in this thickness. 30, 40 nanometers is not. 3M already has let the technology. For example, it's a commercial technique that was developed. I was at NIST, and Daryl Reneker is the person who actually developed that technique when he was at DuPont. Okay, so the machine exists. You can make sheets and sheets of 40, 50 nanometer easily currently, but choice of materials is kind of limited, so this is where we'll have to play the game. Anyway, if this worked, we could take polyolefins as in addition to all the glassy polymers that I showed, make ultra thin films. I think with some creative thinking, all the many of the packed potato chips and what have you already have a metallic layer in them that can act as one electrode. All you have to do is electrode deposit another electrode and test it out. That's what we're going to try. We are actually working with Dow Chemical to on this. This is funded. It started out funded differently by Dow, but they were very interested in what we are doing, and so we are hopefully going to renew our grant from them for this. So I think I've given you the net result is that dielectric strength and mechanical track each other in PP, but not in LLDP. So there's no real correlation. But dielectric strength always goes up with reducing film thickness. It's a kind of a universal behavior. That's very good. Dielectric constant, on the other hand, drops, but the drop does not, it is less in terms of contribution to energy compared to the film thickness. So the film thickness enhancement with decreasing film thickness, the energy storage wins because it's a squared term. And I've shown you that maybe we can make multi layers at the very low thicknesses with that extrusion technology that even exists now and test if, because the weight is going to be the same, whether you have a 62 nanometer film or a 32 times 2 nanometer bilayer. So you're going to gain in terms of net energy storage without adding extra mass is the point. And so if you want a huge bank, you can create, with that low weight because of this strategy. Undoubtedly, there's many more problems to be solved in this, technology going forward. But we think this could be something, for upcycling, take all the waste plastics, polyolefin, and try to use it. And there is my group became extremely huge at one point, but this includes undergrads, masters, and so on and so forth. But Diana Cousins is the one looking for a job right now. She's amazing. She has interviewed a few places, and I want to that's Professor Megan Robertson. We have the Welch Grant on recycling, where we functionalize telecalic polyolefins and try to use them as compatibilizers. I'll stop and answer any questions. Thank you for your interest. I have another meeting in 7 minutes, but I'm happy to answer questions.